Okay, hello. Today I'm going to talk about p-values. What are they good for? So recently there's been some controversy related to p-values and their use in social science research, and so I'm going to talk about that. All right, so one thing that we know is that p-values are ubiquitous. They're everywhere. And this is a video called Dance to the P-Values by Jeffrey Cumming. He's a professor, a retired professor now from the Department of Psychology and Counseling at La Trobe University in Australia. And I really highly recommend looking at the whole video. He's kind of funny, and it indicates some of the problems related to p-values. Very specific interpretation that is mathematically correct and hard to wrap your head around. And so people translate that into their own thinking and they go on and do things. And so Dr. Cumming here is going to have a suggestion for how people think about it.
So let me speculate. I think that usually people think about P in terms of intervals like this. So P less than 0.001, 3 stars, all the way through to P greater than 0.10. And think of P as a measure of strength of evidence. And this elicits significance language from very highly significant down through here, and values between 0.05 and 10 approaching significance. How do you know it's not running away from it as hard as it can go? And we want this language to indicate truth. We desperately want to know about the world and know about truth. There is an effect, or there is no effect, or perhaps even a zero effect. And this evokes emotion. He has affect attached. And it really matters. People make decisions in the world based on values of P, whether you get tenure or not. And so it's central in everyone's thinking about research. But
all right. Okay, so that gives you an idea of how we think about p-values and how important they are. And so as a statistician, I often spend lots of money and time collecting data. And we collect the data, we clean the data, we put the data in the computer, and we press the button. And at that moment, it's very stressful. We're hoping that we get a p-value that's significant so that we have some results that we can publish, and things are exciting. But there has been lots of discussion in the recent decades, in particular in the last year or two, about banning p-values, that p-values are not useful and we should somehow get rid of them. And one of the main places where this has come up is the Journal of Basic and Applied Psychology. So they actually banned the use of p-values. If you send them an article with p-values in them, they're just going to erase them if they publish it. And they discourage highly null hypothesis significance testing. That's where we use these p-values. We have a null hypothesis that says the mean is equal to some number, and an alternative hypothesis where we hypothesize that maybe it's different from that number, maybe greater than that number, or unequal to that number. Okay, and David Taffermau, who's the editor of that particular journal, he says, we believe that the p-value, or this test of p less than 0.04 is too easy to pass, and sometimes serves as an excuse for lower quality research. And he argues that this NHST, or the null hypothesis significance testing, is just invalid altogether. And what they are suggesting is that what they want people to do is they want to essentially people to collect significant amount of data, so large N, and do some kind of descriptive statistics. They don't really talk too much about exactly what they're going to replace all of these p-values with. Okay, so where is this coming from, this movement to ban the p-value? And so what I want to do is I want to start with talking about how we go about thinking about what the p-value is. What is it? What is it good for? And then what are their issues with it? And then how can we go ahead and use them? Okay, so a little bit about the meaning and the history of p-value. So one of the major issues with the p-value is that its definition is hard for people to get their head around. The language is a little tortured. So the definition, or one of the definitions, is the probability of an observed or more extreme result, assuming the null hypothesis is true. So we do this process of assuming the null hypothesis is true. We collect data, and then we see how likely it is that that data came from that null hypothesis. When what we really are interested in doing is showing that the null hypothesis isn't true to begin with. Okay, so where did this idea of the p-value come from? So it came from a long history of probability. Laplace, who's a famous mathematician and did a lot of work in probability, he actually did computations of p-values dating back to the 1770s, where he was looking at the proportion of males that of babies born in Paris, what proportion were males, what proportion are females, and he used this to argue that the proportion of males was greater than 50%. The p-value, as we know it, was first formally introduced by Carl Pearson as a part of his chi-squared test. So we have, there's Carl. Okay? And the use of p-value statistics was popularized the way that we use it today by Ronald Fisher in an important book called Statistical Methods for Research Workers. And there, Fisher actually proposes that p-value of 0.05 or 1 in 20 as the chance of being, as the cutoff that we use to decide, oh, the idea that this data happened just by chance is too small, so therefore we will reject the null hypothesis. So this 0.05 that is used sort of everywhere in statistics comes from this 1925 book. So it's been around a long time. And this is the culprit. This is Ronald Fisher. Okay, and he's also responsible for the F-test and a lot of basic statistics that we use today. Okay, so what I want to do is I want to think about this p-value maybe in a deeper way than we've ever thought about it before. And I want to do it in this, what I call a toy math education example. So my work is in statistics, but also in statistics education and math education. So a lot of the work I do is in that context. And this is not this is sort of a toy example. One could argue with different designs, what might be a more powerful design. But for what I want to do, which is just talk about what the p-value is doing, this example will work just fine. And all the properties that it has, the good and the bad properties, carry over to the other kinds of tests that we do in statistics, the more complicated tests that we do. All right, so we're going to do a pre-post match pair design. So we imagine that prior to giving a teacher intervention, so we're going to teach some students something. So prior to that, we give them a pre-test. Then we teach them something about that content, and then we give them a post-test. So a typical pre-post design, okay? And it's a match pair design. And then we look at the gain. So we look at the post score minus the pre-score, we get a gain. And then we look at the average gain across all those students. Right? And we're interested in testing the null hypothesis that there was no knowledge gain. So this is the true mean gain is equal to 0. Versus there was some knowledge gain, mu greater than 0. Okay, that's a typical kind of thing. And I'm going to simplify this even more than this sort of toy example. That's what makes it even more a toy example. So I'm going to assume that my gains are normally distributed. We have ways in design of our sample size is large enough, we don't really need to assume this. Okay, but I'm going to be doing simulations, so I'm going to assume this because I need to do some simulations. And even further, I'm going to assume that I know the standard deviation of the gains, which is not realistic, and that that's equal to 1. So the whole purpose of that is to make the description of the problem easier, and when I describe what's happening in the simulations, I don't have to go into so many details. Okay, but we still have this test. We have a null hypothesis, we have an alternative hypothesis, and we're interested in gathering data and determining between these two hypotheses. So how do we go about doing that? Okay, so this is the typical thing that would be covered in any intro to statistics class. All right, so under the null hypothesis, the mean is equal to 0. And if the mean is equal to 0, x bar, which is the sample mean, will be a random variable, depending on what data that we get. and it'll follow a normal distribution because of my assumptions, and the mean of that will be 0 because mu is equal to 0, and the standard deviation will be sigma over square root of n. I'm actually going to go further and assume that sigma is equal to 1. It's a little more general. Okay, and then we can normalize this z, x bar over sigma square root of n. If we wanted to do the typical z transformation, we would subtract mu, but in this case, my null value is 0, and I'm assuming the null hypothesis is true, so I don't have a mu there. And this thing will be normal 0, 1, or standard normal. Okay, so then that's sort of the theory behind it, and then we collect data, and from our data we compute the sample mean, and from that we compute what I call an observed version of this z observed. So the difference between z and z observed is that z observed is after I've collected the data, I can compute this actual number. And the z above is this process of saying, you go out and collect the data, and when you do that, that thing will have a normal distribution. So this one is the actual number. All right, and the p-value is the probability under the null hypothesis, which we have assumed for this whole page here, that we get this value or something greater than that. So here's my normal distribution. Okay, here's my z observed, and the p-value is the probability of getting that value or something more extreme. And more extreme in this case is determined by my alternative hypothesis. I'm looking at positive gains. What's the probability I get a positive gain or that I got, or something even more positive? So that's why it's in that direction. And typically we would choose some value of alpha, and we compare either z observed to alpha, z observed to this value, this cutoff value, or we compare the p-value to alpha. And if the p-value is smaller than alpha, we say we reject the null hypothesis, or we say that there's a significant difference from 0 in the data that we collected, or there was a significant, statistically significant gain in learning in my context. Okay, so that's the sort of standard thing, nothing terribly new there. Okay, the one thing that is not discussed in basic statistics classes typically is, under the null hypothesis, this p-value is a random variable because it depends on what data you get. So as you get different samples, the z is going to move around. That's going to create different p-values. And under the null hypothesis, the p-value is uniform 0, 1. And this is generally true for all our kinds of tests, not just this one that I'm doing here. Okay, so what I want to do is I want to use some software called Fathom to do a simulation so that we make sure we understand what all those pieces were. Okay, because we're introducing something that's not commonly introduced in this discussion of p-values and statistics classes. That's distribution of the p-value. And that's going to be important in some of the complaints people have about the p-value. It's called Fathom, and it's particularly good for demonstrating these kind of simple simulations that we're looking at now. So we're doing a simplistic case. It's not very sophisticated software for doing sophisticated analysis, but it is nice for doing these kinds of things. All right, so if you look right here at the top, I have a random normal with the mean mu and the standard deviation 1. Okay, so that's just that model that I have. Okay, and in this first one that I'm looking at, mu is equal to 0. Okay, so we're setting mu is equal to 0. All right, and then I can use this computer to simulate data that satisfies those conditions and see what happens. All right, so the first thing I'm going to do is I'm going to sample cases. I'm going to slide down. Okay, and so as I sample more cases under my null hypothesis, I get gains. So here this dot represented a gain that was over 2 standard deviations above the mean, or just for our cases, our scores, that's our score. That person scored like a 2.3, something like that. All right, it was a gain of 2.3, whereas this person had a gain of negative 1.8. That means they did worse on the post-test than they did the pre-test. Okay. All right, so again, this is on the null hypothesis that there's no mean gain, so we see values above here and below there. And the whole idea in statistics is that we're going to gather one sample and base our decision on that. but it's based on this process where we can get multiple samples. Okay? And so we want to think about what's happening in the simulation, that we may have this data, but it came from a process that could have just as easily produced this data. Okay. So what this software allows us to do is to say, okay, for this sample, I want to compute some statistics. And in the language of this software, they're called measures. But for us, they're going to be like the mean, the z-score that I defined, that z-observed that I defined, and the p-value. So for each sample, I can compute a single mean. That's going to go here. That mean, I'm going to use that formula and find the z-observed value. That's going to go here. Then I'm going to put that on the normal curve, which we won't see, the normal curve, but to spit out the p-value, the area to the right, and that will appear here. Okay, so we have our mean, our z-observed, and our p-value for each sample. Okay, so what this is doing is getting a new sample each time. The line that's straight up is the mean. Every time it computes a mean, it puts an extra dot down here, that's the mean. Then it's computing the z-observed value that goes from that sample, so we're building up this distribution. And over here, we're finding the p-value for each sample, and we're starting to fill out this chart. Okay? And as this goes along, what we're going to see is that this should follow a normal distribution. As we build up enough, we'll actually get to see a normal distribution. This should follow a standard normal distribution, because that's what the theory says is supposed to happen under the null hypothesis. Okay? And over here, we get a p-value distribution that's flat between 0 and 1. You can't quite see it because it's slid over a little bit. But it's between 0 and 1. Okay, and in this case, this line here is at Fisher's special number, 0.05, and all of ours are over here, so we haven't gotten any significant values yet. Okay, let's do it one more time. Okay, so as this fills in, we could do this, and you can set the software so it goes faster if we want. Okay, so we'll see how it builds. Okay, and what we're going to see is this thing is flat and uniform. Okay, and so that means that it has the same sort of probability of being in any of these intervals. So it has a 5% chance of being in this particular interval. So when we say our alpha is 0.05, and we reject for a p-value of 0.05, we're saying that there is a 5% chance that our p-value, that our sample will produce a p-value that's over in this region. Okay, so when I did it over, I got a few that were over here. Okay, if I did it many, many times, 5% of them would appear here. Okay, and if we follow Fisher's rules, the way that Fisher described it, we would reject the null hypothesis, say it's significantly different from 0, even though I've simulated it under the null hypothesis. So those things would be what we call a type 1 error. And lots of statistics and these p-values is set up to control this type 1 error. There's a lot of discussion about type 1. Okay. All right, so then the question is, what happens when mu is equal to 1? Okay, or what happens when mu is not equal to 0? That's really the question. Okay, and so I have this alternative hypothesis. We have mu equals 0. We have mu greater than 0. And I've chosen one of those values to run a similar kind of simulation. So we expect now that we should be rejecting the null hypothesis because the null hypothesis is not true. Because mu is equal to 1, which is in the alternative. Okay, so we have the same setup. Okay, and now we sample data. Okay, and it's a little hard to see in the sample, but there's more data that's greater than 0. More people learn something than didn't learn something because our distribution is a little shifted over because the mean is not 0 anymore. It's 1. That's good. So people are learning things. Okay, so now when I turn the animation off, the distribution, it runs a lot faster. Okay, and we get a distribution of x bar that's now looks sort of normal. If we did more, we would see. Let's do a few more. It ran so fast, we can do more. Okay, this will fill in a normal distribution that's around 1. Okay, then we get a z observed distribution or a z distribution that's no longer around 0 because the null hypothesis isn't true. It's shifted over. Okay, then we get a p-value distribution, which in this case is beautiful. Everything was over in this reject region. Okay, if I increase the sample size, so the first one, I didn't even really talk about the sample size too much. I was using n equals 20. Okay, and here I'm using n equals 200. So let me go up the list a little bit. So that's my sample. There's a lot more dots in my sample, a lot more data points in my sample because n is 200. Okay, we get more information from n is equal to 200. Okay, and what's the effect? All right, the effect on my x bar distribution is that now it's more narrow. It's still around 1, but instead of being as spread out as it was before, it's more narrow because n is 200. And the n was in the denominator of the distribution that goes with this equation. Okay? And the z observed shifts further out. The distribution is centered at a further out point. Okay? And then at my p-value, I basically just got 0 all the time to the degree to which this computer computes. Okay? The number of significant digits that it computes. Okay, so what happens as you increase the sample size is that this distribution is going to get more and more narrow. So it's going to, even though it's around 1, the distribution is going to separate itself from 0. If it was wider, even though it was around 1, it might get to 0, but it's separated itself from 0. And this is how statistics works to reject the null hypothesis, and this is the impact of increasing the sample size. Right? And in some language, you might talk about the increasing the sample size increases the power of the test, the ability of the test to tell the difference between mu equals 1 and mu equals 0. As you increase the sample size, you get a more powerful test. Okay, all of that is good. So why do we use p-value? So I started the talk saying people want to ban the use of p-value, but since 1925, we've been using p-values. So there must be something good about them. Why are we using them for that long? Okay, so p-value calculations incorporate the effect size, which is how, in my little example is just how big x bar was. How different was x bar from 0? Okay, the sample size, the variability of the data into this nice single number called a p-value. Right, puts all that information to one value. Okay, and Fisher thought that this was a way to objectively tell us what the sample is telling us about the data, or what the sample is telling us about the null hypothesis. Okay? Right? In particular, what it tells us is how consistent is my data with the null hypothesis? Because we assume the null hypothesis is true, and then we say, how likely is it that this data would come from that null hypothesis? How consistent is it with the null hypothesis? Okay, and it was designed to protect against the possibility of rejecting the null hypothesis just based on an observed result. I gather some data and I say, oh, there was a difference. It must be great. All right, I taught a class, the students learned something, there was a positive mean gain, it must be great. Okay, okay. Without taking into account the probability model. Right? And the other thing that is really fantastic about p-values, this is one thing that's really good when we teach p-values, is that p-values are all on the same scale. They're on this probability scale, and they're all interpreted the same way. Okay, so if you teach an intro to statistics class, at some point you can say, we reject the null hypothesis if the p-value is less than 0.05 or less than alpha. And that's true for all the tests. Not very much can you say in statistics where it's that simple and it applies to that many things. Okay, and so the p-value, you can compare and understand p-values even for tests that you haven't studied very much about. Statistical tests. Okay, so why, that does all those great things, and my pictures seem to be saying that it worked in my simulation. What's the problem? Okay, so here are some issues with the p-value. The first one is discussed in lots and lots of statistics classes. All right, typically any statistics book will mention this. So there's a difference between statistical and practical significance. We'll talk about that. Then there's this idea of, we're assuming the null hypothesis isn't true. And there are lots of contexts, well, maybe it doesn't really make sense. We'll talk about that. Okay? And the biggest issue is about misinterpretation. There's a particular mathematical or statistical interpretation of what the p-value says, and then there's a particular interpretation that people want it to say, and they are not the same. Okay, and then the last thing that's not commonly talked about, but is one of the issues that led them to ban p-values from that particular journal, is that the p-values have a higher than expected false positive rate. And we'll talk about what that means. Okay, let's first talk about practical significance. Like I said, the power of the test depends on the sample size, right? And so usually you think you want more data is better data, higher end, more powerful test. And that's generally true, except it has this problem with practical significance. Okay, so if, for example, in my toy little example, I say, let's suppose I observed a mean gain of 0.1. If we imagine my data being on the, because it was normally distributed with standard deviation of 1, so imagine it's on the scale from like -3 to +3. Okay? A 0.1 is like a 2% gain. Okay? It's 1/10 of a standard deviation. Okay, so and let's look what happens for different sample sizes. For n, 10, 100, 1,000, 10,000. Okay, so this is an easy calculation of the normal distribution. We can figure out what the p-value would be if we observe that value. Okay, if 10, that's not significant. So you see that difference in a small class of 10, that's not significant. Okay, you see it in a class of 100, it's still not significant. You see it in a class of 1,000, suddenly it's very significant. You see it in a class of 10,000, and it's off the charts significant. Okay, so you can take a very small difference in the true mean value, okay, and you can discover it with n large. But that also means that we'll say that that's statistically significant, but maybe this 2% change gain in learning is not very much. Okay? We haven't talked about the context at all, but if it took a whole year to teach them and all they learned was 2% more than they knew at the beginning of the year, that would not be so hot. Okay? And this practical significance is very context dependent. It depends on the context you're looking at. It's based on what your expertise is, what you know about what's important about this problem. Okay, so statistically significant differences need not be practically significant. So if this is not practically significant, I can make it statistically significant if I see it in a big enough sample. Okay, and for this reason, it's really not enough to just report the p-value. As a made-up example, this is a made-up example. White et al., that's me, 2016, reported significant gains in learning, p-value less than 0.05, using statistics aerobics method for teaching hypothesis testing. Okay, so we have p-value less than 0.05, so it matches the magic criteria, okay, but we don't know anything else. In particular, we don't know the sample size, we don't know the context, and we don't know whether the effect was really practically significant or not. Okay, so that's commonly discussed in statistics classes. All right, the other one is, can the null really be true? So, just to make it really clear, let's suppose instead of doing the one that I said, let's suppose we did mu equals 0 versus mu not equal to 0. And remember, mu in my little example is true mean gain. Okay, so this means that we have an intervention, students are in class, they're doing something, and from pre to post, the null hypothesis means nothing happened. Okay. That seems kind of unlikely. Something might happen. Maybe it wasn't practically significant. Maybe it wasn't big. But something, right? And when you think about it, we have this number line from minus infinity all the way to plus infinity. And the null hypothesis is associated with just this one little value. And the alternative hypothesis is associated with all of these other values. So it's really unlikely in lots of settings that the null hypothesis would actually ever be true, meaning the mean mu is equal to 0.000000000 and so on. Okay, so that is one of the complaints that people have about the p-value and this misinterpretation. Okay, so this has to do with how we interpret it. So we have to remember the definition of the p-value. Assuming the null hypothesis is true, it's the probability of something. Okay? So, assuming the hypothesis is true, this is a conditional probability, the straight line means given. So given that the hypothesis is true, we're finding the probability of getting that particular observation or something more extreme. Okay. And what people want it to say is the probability of the hypothesis given the observation. And those two conditional probabilities are not equal. Okay? In the frequentist case, it really doesn't make sense. Right? So the parameter is unknown. This mean is unknown, but in the frequentist case, that's how most statistics is taught, we think of the mean as this fixed unknown value. So what am I talking about? Okay? So we had the mean equals 0 versus the mean greater than 0. That was the toy example I'm looking at, right? And the mean is a number. So I could ask you to think of a number, and don't tell me what it is. Think of a number, don't tell me what it is. Okay? And you have a number. That number is fixed as long as you pay attention to the rules. You're supposed to think of a number and stay on it. Okay? And so that means either the null hypothesis is true or the alternative hypothesis is true for the number that you have in your head. There's not a probability issue there. Okay? So the probability of the hypothesis given the observation is either 0 or 1, depending on which one the fixed number happened to be. Okay. In the Bayesian approach, they actually think of the parameter as a random variable. So they think of the mean as a random variable. And we're going to look at a very simple example of a Bayesian approach later on. Right? So in that case, you actually can think about the probability of the hypothesis, because the mean is not a fixed number, but a random number. The mu is not a fixed number, but a random number. And so this kind of makes sense, but it's not equal to what the p-value is computed. So this means when we talk about the p-value, we're saying, assume the null hypothesis is first, talk about the probability of the data, not the other way around. Okay, in one of the articles I'm going to talk about, Selke et al. 2001, they say the standard approach in teaching of stressing the formal definition of a p-value, which is the one I've given you, while warning against its misinterpretation, saying that those two things are not equal, has been an abysmal failure. Okay, so as a teacher, I know this, so I teach statistics, I teach this definition of p-value, I ask students at the end of the year to talk about p-values in context, and they give me not the left one. Okay, when I was thinking about this talk, I went online and I looked at in the The journal Nature, they have an online version that has sort of the journal plus the magazine part, and they have an article about this psychology journal bans p-values. It's about that psychology journal I was talking about. This is the website. And when I got to it, because it was earlier, so it was earlier last year, when I got to it, there was a correction on the bottom. And it said, so it has the article and it says, clarified. This story originally asserted that the closer to zero the p-value gets, the greater the chance the null hypothesis is false. Okay? Which is exactly the misinterpretation. So here we have an educated person working for a science journal talking about the controversy about p-value and getting the interpretation of the p-value wrong, because it's just tempting to think about it that way. The last thing of the issues I wanted to talk about is this higher than expected false positive rate. And this has to do with thinking about what the distribution of the p-value is, not under the null hypothesis, but under the alternative hypothesis. Okay. And so this is continuing the video that I showed you earlier. And so he does a simulation. He doesn't do my simple example. He does a simple two-sample example where the null hypothesis and the alternative hypothesis are close to one another. And he simulates the data under the alternative hypothesis. Okay, so similar to what I did. But when I did it, I said mu equals 1, and my null and my alternative were far apart. Mu 0 and 1 were far apart from my example. He's doing it for where they're a little bit closer. Okay. And what he does is he has a program that he's built in Excel where he computes the p-value, he simulates, he computes the p-value, and he has a little symbol for the p-value, depending on which one of those regions it fell into. The less than 0.01, I'm super happy, I'm going to get tenure, or greater than 0.10, oh man, I'm sad, I'm not going to get anything happy. And he calls this the dance of the p-values. It even has music associated with it. So what's happening here is we have our two distributions of blue is the null value or the control value, and the red is the experimental. He's looking at that difference, so they're pretty close to one another. And down here we have symbols for what happens depending on what the p-value is. If the p-value is small, we're happy, yay! Okay? If the p-value is large, we're weeping. And we have things in the middle, going with each one of those categories. Okay? And the point is, when you watch this happen, you see a mix. You see these purple ones, these yellow ones, these pink ones, and these red ones. Okay, so what he says is, if you replicate the experiment, this particular experiment, and I do it, and you do it, we're very likely to get different p-values. Maybe I'll get the red happy guy, and you'll get the purple blue sad guy. And the context is exactly the same, so that the p-values vary a lot more than one would expect. Okay? And when we're talking about a false positive rate, what we mean is we reject the null hypothesis, but we shouldn't have. And we need some way to talk about that. And the easiest way to talk about that is in the Bayesian context. So that's what I'm going to do. Okay, so this is a paper I've already mentioned, Selke, Bayari, and Berger. Okay, and they are Bayesian. Berger is a Bayesian statistician at Duke. He's probably the most famous Bayesian in the world. Okay? And in that paper, they think of this fairly simple example. So in their context, they're actually thinking of them as drugs that we're looking at the effectiveness of the drug. But to just relate it what we're looking at teaching methods that are ineffective, so that students don't gain any knowledge. Okay? So that's mu equals 0. All right? And teaching methods that are effective. And for this simple example, we're taking all the effective ones to have the same effectiveness. So mu is equal to C. And I'm going to change C, but I'm going to just imagine 50% of them are 0 and 50% of them are C. So what could these things be? Well, maybe teaching with the computer using this software. Maybe teaching with the computer using that software. Maybe all these different ways that one can teach mathematics, statistics, or whatever topic we're talking about. Okay, and the idea here is we have all those possible teaching methods. Half of them don't do anything, and half of them are good in the exact same way. In our simulation, what we're going to do is we're going to flip a coin. And the coin flip is going to determine whether we get an ineffective one or an effective one. Then, I'm doing this via simulation. We're going to sample, and I'm just doing n is equal to 20. All of my sample sizes are going to be n is equal to 20. I'm going to gather my data, I'm going to compute the p-value just like I've shown you. Okay, so this is exactly what I've done before. Okay, and then we're going to repeat this whole process. So we're going to flip the coin, gather the data, compute the p-value. All three of those steps over and over again. And I want to do this 50,000 times. Okay? I want to do it lots of times because what I'm going to do is then look at what happens when the p-value is in little tiny ranges. So I need lots of examples so that this will work out for me. Okay, so when I'm done doing it 50,000 times, I'm going to look at the p-values that fell in a particular interval. So when I do this, the ones from the left, where the teaching method was ineffective and mu is equal to 0, those p-values are supposed to be uniform. So 5% of them will be between 0 and 0.05. And 95% of them will be bigger than that. And I'm going to pick a range, like 0.04 to 0.05. And I say, okay, how many had p-values in there? Out of my 50,000 samples that I did. Okay. And then I'm going to look at those that had p-values between 0.04 and 0.05. They could have come from either place. From over here on the left, and it was a type 1 error, or from here on the right, and it was a correct decision. We're supposed to reject the null hypothesis there. Okay, the C that I'm choosing is greater than 0 for all of these. Okay. All right, so what we're doing is, in practice, when you do statistics, you gather your data, you put it in your computer, you push buttons, you get a p-value, you compare to 0.05, and then that's it. Okay? And you reject the null hypothesis and you hope that you're right. Okay, in this context, we didn't just do that once, we did it 50,000 times. And we're going to see if you were right or if you're wrong in this way. Okay. All right, so what I'm going to do is look at the rate of false positives, so that I'm going to look at the probability that it comes from H0, from the null hypothesis, given that the p-value was in a particular range. And my ranges are 0 to 0.01, 0.01 to 0.02, 0.02 to 0.03, 0.03 to 0.04, 0.04 to 0.05. So all of them are in the reject column. Okay? And so if they came from the null hypothesis, that was a type 1 error. If they came from the alternative hypothesis group, the 50% over there, that was a correct decision. And I have a mix of them. Okay? And I'm looking at that mix. What percentage of them were from the null hypothesis? And those are false positives. Those are the ones that make me sad, because that means the p-value is less than 0.05. So I'm saying I'm rejecting the null hypothesis, but it really came in this simulation from the null hypothesis. Okay. All right, and then I have my C value, which is 0.1, 0.2, 0.3, all the way to 1. Okay, so that example that I simulated before, that was C equals 1, where we just rejected the heck out of things. Okay, so let's make sure we understand some of these numbers. So let's go down. The interesting case is when you're on that edge, 0.04 to 0.05. Okay, so we reject using Fisher's criteria, but just barely. Okay, So when it's 0.1, we see that about 36% of those that landed there were from the null hypothesis, and the rest, 64%, were from the alternative hypothesis. All right, so you might think alpha is 0.05, this should be 5%, but it's not 5%. 36%. Okay, so then as the C gets bigger, oh, this thing is doing better. Okay, so when C is 0.3, then only 17.7% that just barely rejected were really from the null hypothesis, and the large majority of them were from the alternative hypothesis, the C equals 0.3 group. But then look what happens. It starts going in the wrong direction. Okay, so the one I'm going to look at is this column, this one and this one. Okay, so when the C is 0.9, so that's a pretty big difference, and I look at those p-values that just barely rejected, 78% of them are from the null hypothesis. Very few of them are from the alternative hypothesis. This is extremely counterintuitive. We would expect that if I'm testing a case on a computer where I know the alternative hypothesis is true, and I get a p-value that's less than 0.05, surely it must come from that version, the alternative hypothesis, C equals 0.5. But it doesn't happen. Why? Okay, so maybe we don't understand what these numbers are representing. Okay, so here is a histogram of the data, the p-values that we get from the simulation. Okay, so these are the ones that end up with, from the null hypothesis, mu equals 0, and these are the ones when C was equal to 0.3, so mu is equal to 0.3. Okay, so under the null hypothesis, it's uniform, as expected. And under the alternative hypothesis, it's squished close to 0, as expected. That's what we want to see. But what are we doing in that table? We're looking at, I made my bars different lengths, so that different widths, so that I could do this comparison to match the table. I'm looking at this bar. This is the bar that's 0.04 to 0.05. Okay? And this the area here tells us what percentage of all of the simulations ended up here. Okay? And this one tells us what percentage of all the simulations ended up there for the null. And what we're looking at here is essentially the red bar here, the short little bar, divided by this one plus that one put together. We're putting the red bars together and we're saying how many of them came from the left side, how many of them came from the right side. Okay? And more of them came from the left side. I'm sorry, more of them came from the right side, fewer of them came from the left side. Okay? So the probability that if the p-value is in this range, that it came from the null value is pretty small, because this bar is small, and this bar is pretty big. All right, so what does that one correspond to? Let's go back to our table. That corresponds to this value right here, 17.7%. So that's a small percentage because the bar on the left is short compared to the bar on the right. Okay? And what happens over here when it's 78 and 71.2? Okay, so my scale is all crazy now. Okay, so this is still flat and still uniform, just like it was before. Okay, and I've actually colored red not the 0.04 to 0.05. I've colored red the 0.03 to 0.04 because over here I couldn't even see the 0.04 to 0.05 on my. Okay, so again we're doing the same thing. We're comparing this little red bar to the red bar that's there. You can barely see the little tiny red bar there. Okay? And we're putting those together, just looking at those. And we're saying, well, if we put them together, how much of it came from the left side, how much came from the right side? Well, a lot more came from the left side. Okay, because we have half of our data, or sorry, half of our samples came from where the null, from the ineffective model where the mu was equal to 0. Okay, and so 5% of those end up over here, or 1% end right there. Over here, our p-value is squished up against 0, so it's very tall against 0, it's very skewed. There's hardly any here. So in this particular example, if you happen to get a p-value that's very, very small, like 10 to the minus fifth, oh, that's from this side, because that's this really tall part. But if you get a p-value that's just barely significant, like 0.044, there's nothing there. It's really from this side. And so this means that the way we think about p-values depends on the context in which we're doing the testing. Okay. Oh my goodness, so what do? Do we just throw it away? Do we not do p-values at all? Maybe. Okay, so the video from Mr. Cummings, he suggests looking at confidence intervals. He thinks confidence intervals are a better alternative. And it's a perspective. It has the same data, it has the same statistics, the same theory, except it's this perspective of estimation instead of testing. Instead of saying it's this or that, we're saying it's over here. Make a confidence interval, you can see the estimate of the parameter, and you can see a measure of the uncertainty in the parameter in the confidence interval itself, or in the margin of error. Okay? And it's easier to distinguish between different cases where we might reject the null hypothesis. So I have a picture for that because you wouldn't know what I'm talking about. So if we have our point estimate plus or minus our margin of error, that's our typical confidence interval. Not all of them, but typically they're like that. All right? So here's my point estimate. And this line here represents my confidence interval, a very generic case. Okay? And I'm comparing it to 0, because that's what we were doing in our toy example. Okay, I can have a wide confidence interval that just barely misses 0. I can have a narrow confidence interval that misses 0 but is really close. Or I can have a narrow confidence interval that's far away. Of these three cases, this is the one that makes us happier about rejecting the null hypothesis. We feel like, yes, we're really rejecting the null hypothesis. And when we see this picture, if we see this one or this one, so we know what's going on. We have a sense of where our estimate is, what's the actual effect, okay, and we have a visual of the uncertainty. How much uncertainty is there in that estimate? This one, there's a lot of uncertainty, that's why it's wide. These, there's less uncertainty. So typically, this would be a small sample size, this would be a large sample size, and this one might be the case where we would have statistical significance, but not practical significance. The last thing that is often recommended, especially in educational studies and sociological studies, is to report the effect size. So the effect size is something that says how big a difference was there in some standard-ish, definitely-ish units. Okay? So if we're comparing two groups, this might be a simple control treatment situation, or it might be a K sample where we're doing an ANOVA or an ANCOVA, and we have like 5 groups, but we're comparing them 2 at a time, right? Then the effect would be the mean difference between the two groups divided by a corrected standard deviation. So if we look over here at this picture, our data coming from 2 different populations, each of them sort of normal as they are in my picture here, okay? And we're not looking at the standard deviation of the whole group together. We're imagining treating them different. This is group 2 and group 1. Maybe this is the treatment and this is the control. And this is the means, and we're looking at the mean difference, that's in the numerator. And we're looking at the standard deviation that says how spread out are they within the group. So that's what I'm talking about when I say a corrected standard deviation. So in this 2 sample case, if you've looked at these 2 sample problems, they have something called the pooled standard deviation. That's That would be one of the possibilities that we're talking about there. Okay, if we were doing a regression model, so, a kind of multiple linear regression model, and we had a treatment variable that's 0 and 1. Treatment is 1, we're in the treatment, 0, we're not in the treatment. This beta 1 represents the effect. What is the effect of being in the treatment? Okay, so we would look at the estimate of beta 1, right? And then we would, in most of these models, we have an error term that we assume often is normal. It has mean 0 and it has some standard deviation of that error term. And we have an estimate of that. In lots of cases, it's the mean squared error, right? And so our effect would be something like beta 1 estimated, that would be hat, divided by sigma estimated. And if you look at different places, there's lots of different ways to estimate what's the right version of sigma hat to put in here to measure the effect size. Okay, so that's the idea of the effect size when comparing groups. So in this one, we're comparing the treatment to the control. Okay, if we just have a simple two-sample problem, we have a famous one that's called Cohen's d, which is the mean difference divided by s, where s is the pooled standard deviation. It's like the first example I was talking about. Okay, if we're looking at linear modeling, like multiple regression, but maybe we're not interested in the effect of the treatment, we're interested in the effect of a continuous variable, then we would look at the effect as the change in percent variation, or the delta r squared, or something like that. So you imagine modeling it with that variable in there, and with that variable not in there, and looking at the difference in the variation expression. Okay, so guidelines for using p-values. So this is a mix of something from Jim Frost, who does a blog for Minitab, my ideas, and Mr. Cummins, who had that video. Okay, so one of the things about if we're going to use p-values, we should think of p-value as like the first step, not the last step. So one thing we find from our little simulation is that exact p-values matter. If the p-value is 0.004, that's better than 0.044. Okay? Another one that we want to think about is replication. We want to think about what is the study doing. So Fisher himself said, a scientific fact should be regarded as experimentally established only if a properly designed experiment rarely fails to give this level of significance. So it indicates the idea that you should be doing this experiment and doing it again and again and again. Not just the sample size, but maybe in different conditions and so on. Okay? And that it's important to not, what we say in English, cherry pick, which means pick the best ones that are significant and ignore the ones that are insignificant. We should do all of the studies and see how often they're significant and how often they're insignificant. Because we expect to get both of those no matter what's the truth of what's going on. Okay, effect size matters, right? And so we should present the effect size and we should discuss its practical significance, right? So what effect did we see? What's the impact on the context that we're really talking about? Okay, we should probably report confidence intervals. So the point estimate plus or minus the margin of error, or the point estimate plus something that lets us compute the margin of error, so someone can make the confidence interval on their own. Okay, and this idea of alternative hypothesis matters and subject area knowledge matters has to do with what is it that we're testing. In my simulation I said, well, half of those teaching methods were ineffective and half of them were effective. But if I know a lot about the context, if I know a lot about teaching and what works, maybe the thing I'm testing has a better chance than being half-half. And by knowing that, then I can design a study that's testing something that has a good chance of working. All right, so what this says is that the statistician can help you design the study, how you're going to collect the data, can help you tell you what to compute once you get the data, all right? But the statistician can't just do it all. The person who's actually familiar with the context has to know what it is that we should be testing. What teaching method should we be looking at in my context, or whatever treatment we should be looking at in your context. Okay, so I will give you a copy of these slides. These are the two things that I refer to in addition to that video. So this is the blog, and this is the paper that looks at it's called Calibration of P-Values for Testing Precise Null Hypothesis. They have a description of that simulation, plus they have some calculations on some formula that you could report that might be better than just the p-value. But it's a little complicated, so I'll leave that for another video. All right, thank you very much.